So anywho, we'll crack into it. Starting with our outline, what is CFD? We're gonna go over that first. We'll talk about some important fluid foundations. I included that for those of y'all that maybe haven't taken fluids yet or don't know as much about it. Yusuf, I think you already should know because you're in like flight mech and all of that. And then we'll talk about a 2D problem and a 3D problem. And then I can give you guys, I probably will send you guys the files that I used, not only to make the simulation, so like the CSV and the object files. Actually, I use STL, that doesn't matter. So that you guys can do it on your own at home and then you can follow along. Optimally, we would be in a computer lab and you could follow with me, but alas. So I'm recording this and I'll put it on YouTube so you guys can like look at it later. And they're smiling at me because they're trying to get me to start a YouTube channel. Anyway.
Why not? Just reuse the modeling methods.
I'm just gonna add this to that one because it's like it's just random videos. I used to have my measurements videos on there too, but I took those down because those were so cringe. That was during COVID days, so we had to do it. Anywho, so CFD, what is CFD? ANSYS has a definition that's actually surprisingly not as formal as I would have expected from ANSYS. But effectively, what you're doing is you're finding out the details of how fluid flows. Could be a liquid, could be a gas, and how it flows in a certain scenario that you're interested in. And it utilizes specific computational tools to solve it, because most of the time you either can't analytically solve these problems, or it would be insanely difficult to just do it yourself. Either one of the two. Technically, Navier-Stokes, the equations that this is all based off of are analytically unsolvable, hence why we have to use tools to get close. And yeah, so some of these tools include the use of finite difference method. If you take in modeling methods, like at least one individual here has, you have heard that term 5 bazillion times because it's really important.
Every class.
Every class, yep. Every single one. It's super important. It's built off a Taylor series, and you're just approximating derivatives, and that's all it is. It's really easy. We love it.
I actually hated Taylor series.
I did too when I took calculus, but then finite differencing makes it make more sense, if that makes any sense. So when you get to it, because you probably take it either next year or 2 years from now? Next year, probably, right?
Yeah, I'm going to do it, I think, either next fall or spring.
Yeah. It's not bad, especially when you, yeah, anyway, that's a tangent. But effectively, you know, the idea is you have some region of interest that you want to know how fluid is either flowing through it or around it, depending on if it's internal or external flows. So it could be a pipe, or like this meme of your aerodynamics of a cow, that's an external flow problem. And different solvers may approach doing this differently, but in total, they're all kind of doing the same exact thing. So our fluids foundations, this is snatched from NASA because I like how they write theirs out. So fluids problems are almost all easily governed by these equations, which we call the Navier-Stokes equations. They look hideous because it's a whole lot of calculus. It's a whole bunch, it's really partial differential equations and a system of them if you really look at it. So you don't have to know how to use these to do CFD. It is important to know, however, the basics of that. Your Navier-Stokes equations, which govern your fluid system, is just conservation of mass and conservation of momentum and conservation of energy. That's all it boils down to. Doing the math to solve them, hideous. But everything that's going on behind the scenes when you're doing CFD is these, but you're using tools like finite difference to approximate the answer to each of these. So ugly on the surface, but you don't have to do it, which is why we love CFD. Yay! Because you don't have to do it. It does it for you. Or if you take a CFD class, you have to program your own CFD solver, and then you also have to do it. Not super fun, but interesting nonetheless. So further, another thing ripped from NASA, some other important concepts to know are things like Reynolds number, which, as it shows, can you see my mouse? No, you can't. Is there a pointer tool on this? Hey. So right here really is what you want to know with your Reynolds number. It is effectively a ratio of your inertia to your viscosity. So it's saying how much is like the speed of your fluid and how much inertia it has, how much is it dominating versus your viscous effects, the things that slow it down, that are more impactful at, like, say, in an example, if you have flow through a pipe, which is kind of what we do with cardiovascular stuff, the walls are going to have more of these viscous forces because it wants to stick to the wall because the wall is not moving, but your fluid is. And so it's a ratio of like effectively saying, how much inertia do you have? How fast is this thing moving? But also how viscous is your fluid and how these forces are interplaying with one another. And what does it tell you? It can give you a clue as to whether your flow is turbulent or laminar. So if a flow is laminar, you can think of it, it's on that top right. Oh, my cute little laser pointer. You can think of it as, they say it's like laminae or however you pronounce it. It's just smooth flowing. Everything's flowing in what they describe as sheets. If you guys have ever seen those video clips of like something pouring through a spout and it looks like it's not even moving, like it's like solid because it's flowing so perfectly, that's laminar flow because it is streamlined. The formal definition is something along the lines of, if you have streamlines, none of them cross, especially out of the boundary. Really, it's just that it's all perfectly smooth in its flow. And those are when it's more dominated by viscous forces, less inertia. So it's going to have a lower Reynolds number. Turbulent flow, on the other hand, jumbled all over the place. Most real life flows are turbulent because that's just how the world is, especially with like water. It's not that viscous. And so in the case where your Reynolds number is sufficiently large, so if it's above 3,500, but really above 4,000, you're going to have turbulent flow. There's also other cases where you can have a lower Reynolds number and there's still turbulence, but that's a more heavy fluids topic that we don't want to talk about.
But is this only for internal flow? The Reynolds numbers.
The Reynolds number
3,500, 4,000.
generalization. In every fluids class, Lucy's fluids class, he always just said in general, that's your rule of thumb. I can't tell you for external flow because I'm not aero, so I never looked at external flow. I've only ever looked at internal. So for you, I might want to, like, if you're ever doing an external flow problem, I would verify that for external flows.
No, it is like over around 400,000.
It's a big number.
Yeah. Really big number. So I just want to.
And typically, like in real world situations, especially aero, when you have air as your fluid, which is really not viscous, you're gonna have some really big Reynolds numbers. And most of my aero friends that I've talked to, almost all of their applications, there's almost always turbulence, and so you have to include a turbulent solver, which is its own can of worms.
Oh really?
Turbulent solvers they're a lot.
But it's still through like CFD, right?
CFD has turbulent solvers built in that you can add. We can talk about it when we get to it. Yeah. But it's a lot of statistics if you get into the nitty gritties of it, which is gross in my opinion. I hate statistics. But another important thing for specifically this lesson today and our examples that we'll look at is this cute little bottom right guy here. So if you have an internal flow and you're introducing liquid into a pipe, typically it's going to start out, you have a uniform flow coming in and it's going to have this flat profile. All of the fluid flow should start out same velocity. But you have I keep forgetting I have a cute little pointer. This little line here and this one here are going to be your boundary layers that grow as you go further down through the flow of the pipe. And this is like kind of an idealized case here. But in general, for internal flows, this counts. So you have some turbulence and turbulent interplay in this boundary layer as it grows in here, but as it continues on through the pipe, it will eventually become fully developed and should become laminar. It's just in this region, your developing region, your entrance region, you're going to have some turbulence, especially in this boundary layer. But what I want you guys to know, because you're not quite a few of you guys haven't taken fluids. What I want you to notice is just this pattern here of it starts out with this flat profile. And so this is like the velocity profile, how fast the fluid's going. And it turns more and more into a parabolic curve. So this specific shape is what it ends up becoming when it's fully developed in laminar. And you can calculate how long this region's supposed to be. There's an equation for it. It's actually kind of simple. But I'm not going to make you guys worry about that for now. Just note the pattern because we're going to look at an example that has this. And then I don't know why I put this after those. Probably because I was doing this at midnight last night. Other than just to like reiterate, I guess, what the Navier-Stokes equations are. Continuity equation is your conservation of mass. It's effectively saying like your gradient or your divergence out of your field, so flow that's coming out, your net is 0. It's nasty. It's just conservation of mass, really all that is. And then conservation of momentum. This is an easier way to write all 3 dimensions in one. It can also be rewritten into other scales or other coordinate systems, but that's another gross thing to talk about. So yeah, that's all the background. Does anybody have any questions, comments, concerns? No? You guys feel like that kind of made sense? Did I take it down enough in level for it to be understandable? Excellent. And then this should help both of you two when you do take fluids.
I'm in it right now.
Yeah, but it hasn't really started, has it? It's syllabus week. Do you
I,
have
well, we
Boosie?
did start.
What's that?
We started pretty fast.
Really? Who do you have, Boosie?
I have Mizundar.
Mazunda for fluids.
Yeah, he's doing fluids now.
Yeah, I got blessed.
Mhm.
Honors.
I took him for thermal and heat transfer. I thought like he was only.
Oh, Mizundar, you took him for? Yeah. He's also doing grad classes, I think, now too. He's doing a lot. But it's because people like him, so.
Well, you're lucky that you don't have asthma.
I actually
I heard
did,
that's traumatic.
and then it switched.
Good.
Her author was good though.
I've heard you learn a lot, but anyway, I had Boosie, so I.
No, asthma is ruthless. Honestly.
Anyway, for the record, that's redacted. These names have been redacted. This is all in Minecraft now. Anyway, so we will crack into it. First problem we'll talk about is a 2D problem. Imagine, and I don't know why I didn't put a graphic here, I probably should. But you have flow between parallel plates. So you imagine you have some channel that's created by these 2 sandwiched plates, fluids coming through between the 2 of them. Kind of like that cute little graphic I showed you guys here. This is a similar kind of setup. And so we're given some density and viscosity. This is supposed to be similar to linear blood properties. So you'll have a density of 1060 kilogram per meter cubed, viscosity, centipoise, and then a specific distance between our plates and a length. So we'll hop into hello. Okay, it's being weird. Probably because I'm screen sharing. But so Star-CCM, we love it. She's great. People use ANSYS too, ANSYS Fluent. I only have a little bit of ANSYS experience. It seems cool too. I've heard it's been really advancing in what it can do lately. Like it has better FSI support. But I get stuck in my ways, and I like this one. Also, I don't like that ANSYS opens up a new program every time you want to use a separate module in it. I find that really annoying. But we also have other reasons why we use Star as well. But this is what it looks like when you open it. Everybody has access, all of you guys do, because we have a student license. And it's a full license, so it's actually pretty good. You have to go to mycecs.edu, I think, or .ucf.edu or something like that. It's mycecs is what it is, though. You log in, and then it has the license to use it. You can get it on your personal computer. Also, all of these computers should have it. Granted, the best computers to use are really just that one, the one that's in the corner over there, if it still turns on. I haven't touched it in a while because that's usually the computer Jim uses. And then we finally were given, Kyle relinquished his computer because he's in North Carolina, so he doesn't use it. But it's having some display issues, so I just had to give it over to IT to get reformatted. But hopefully we'll get that back soon. And then you guys can use it too, because it's actually nice. It's the same one that I have over there. So, but also fair warning with that one, sometimes this guy, his name's Abu, he graduated, but he still kind of works with us, but like also kind of doesn't. I don't really know. He works for John Deere, which is kind of cool. I don't know what he does. Something computational, I'm assuming. But he logs in remotely to that computer sometimes, so it may not always be available. And he'll probably call me if one of y'all tries to log in and kicks him off. But I wouldn't worry too much about it because I don't know what he's doing. He should just be using the cluster, so I don't know why he needs that one. Other than for when he calls me to tell me it got turned off and I have to turn it back on. But anywho, so we'll crack into it. Everybody ready to get started? So new files, just this cute little new file button. Everything should just be default. We're running it a serial process, so we're only running it on, or I guess we're not running it in parallel to be run across multiple CPUs or multiple threads. We're just going serial here. All this server stuff and everything else should be default, and you don't have to worry about this command thing either. It gets auto-generated. You can just hit OK, and wait for it to start. We shouldn't take too long. I might threw an error there for a second. And anywho, here's what she looks like when you get it started. My first step that I always try to do, well, one, you're supposed to save, so I'll be good and I'll actually save it, even though my thing keeps defaulting to my OneDrive instead of my actual drive, and it drives me nuts. So I have to go through this. So now you guys are getting to see my folders. Oh yeah, I stuck it on a new folder because I forgot to rename it. Tutorial 2. Save. Okay. So step one, actual step one, is you want to go File, Import, and this is where we're importing our actual region of interest. These are typically STL files, so there's a bunch of different object files. If any of you guys are familiar with CAD or 3D printing, you'll have heard STL, OBJ, SolidWorks, there's a couple of other ones. There's like XD, something like that. Star can support a couple of different ones. I always just use STL because it's easier to work with. You can export that file type if you use SolidWorks, and yeah. And also, you 3D print with STL files, and I have a 3D printer, so I'm just comfortable with it. So in this case, actually, I think I goofed. If we're doing the parallel plate one, we're actually going to make our own geometry. So Star is capable of doing CAD itself, which is actually pretty neat. It's not as visual as something like SolidWorks is. But so in the case, if you have two parallel plates, your zone of interest is actually going to be that inner bit, right? So it's just going to be effectively a long cube, or a long, rectangular prism? Is that technically correct? What is the name for when it's a cube but long? Does it have one? I'm forgetting my geometry.
Cuboid?
Is it a cuboid?
Was it?
I don't remember. Anyway, it doesn't matter. Long cube is what I'm going to go with. Long cube. And so we're going to let the first corner just be at the origin, so 0, 0, 0. And then what did we set our parameters to be? We said 20 millimeters. So we'll let it be a 20 millimeter square area. So we'll say 20 millimeters. And then if I remember correctly, it has to be set up a certain way if you do 2D. And I want to say it has to be along the y-axis. We'll find out here in a second though. 20 millimeter by 20 millimeter by 1 meter. And then that doesn't show anything because we have to go new scene, geometry. And there it is. Probably should have a mouse for this because this will probably make my life a lot easier if I do, but that's okay. So here she is. I appreciate your enthusiasm for our long cube. It's kind of anticlimactic, but you know, it's nice in a pinch if you have a simple geometry that you're trying to work with. But for now, this is our region of interest. It should be 20 millimeter by 20 millimeter by 1 meter. And now you want to split up our surface. It's easy in this case to do it by patch because it was made in here. And we want to name all of our walls. We should do, let's see. We want to know what at least establish our coordinate system. So let's see. We'll do plus y. And then we'll let that be vertical. Okay. So we'll say that this guy, it's like kind of arbitrary, but it's easier if you mentally establish what your frame of reference is. So we'll say that this is the top surface. If you click on it, it'll highlight it pink, but it also will highlight it here. Create, and then now it's magically gone. Here, we'll say that this one is wall 1. Create. Click on this guy. We'll say that this one's the inlet. Create. Now that one's gone. Okay, sweet. It does let me click it. This is wall 2. Create. And then this guy is going to be the bottom. And then it won't let you rename that outlet from here. So you have to just go back here and then rename outlet. Ta-da! So now we have named all of the faces of our cube. I know, gorgeous. Next important step. So you want to assign parts to regions. Make sure that this is selected, our block here. A region for each part, a boundary for each part surface. Apply. Close. So now under our regions, we should have our block, which is our region of interest, and it should have each one of these faces that we've had and given a name. By default, it makes them all walls. You just have to go in here and change them. So bottom is a wall. Inlet is not. Inlet is going to be a velocity inlet because we said back here, right, that it's got an incoming velocity of 0.3 meters per second. So that's a velocity inlet. Outlet, we'll just let it just be an outlet for now. There's a bunch of different types. Something that's important to know, right, is so we saw those Navier-Stokes equations, right, and they have a whole bunch of variables. Well, effectively how this works is you're saying, okay, I'm giving you all of my boundaries. I know some quantity where the flow is coming in. So whether that be your mass flow, the velocity of the flow, whatever, some property of your fluid at the inlet where it's coming in. And you also know some property where it's coming out. You can have multiple outlets. You can also have multiple inlets. But the point is, these two values have to be different types of values. You can't have two velocities or two pressures or two mass flows. They have to be different quantities because otherwise you're not giving the equations enough information. You have to give them at least two. And then your walls have their own properties, but they're not necessarily like a detailed boundary condition. We're just saying that this is a wall and they have their own conditions. But yeah, and so when you're giving it these properties at inlet and outlet, it is then able to chunk by chunk solve those Navier-Stokes equations working into the inside. And it's solving it chunk by chunk. And we'll see how it gets turned into chunks in a second, but that's the mesh. So inlet, outlet, we've established these. We'll give them quantities in a bit. That's in general how you set the geometry and all that stuff up. And then
Are we assuming steady flow?
we'll get to that in just a second. The next bit you want to do is you go under operations, which is I think under the geometry folder. It's down here. New, and we're gonna do this 2D first because it's a lot easier to do 2D. So we'll say badge for 2D meshing. Select it and you hit execute. Okay. And now that just told Star, hey, this is going to be analyzed in 2D and you're gonna mesh it in 2D. So prepare for it. And then now we do another one. This one's mesh. Now this one is 2D automated mesh because we don't want to do it ourselves. Make sure our guy's selected. There's a bunch of different options. You can read about them if you're really curious. I typically go polygon. polygonal mesher if you want to go crazy. And then for my optional volume, I usually go prism layer, because if you do prism layer, I'm trying to like not give so much detail to just completely overwhelm you guys. But effectively, what prism layer does is it creates a separate, it's not separate per se, but it modifies the mesh around the walls and the inlet, where you know that the details of the flow are rapidly changing. So you know how I showed you guys in that over in this cute little graphic down here, how you have this boundary layer and there's some like turbulence and stuff going on in here. Well, this is rapidly changing, and the details of the fluid flow in this region are rapidly changing, and they change rapidly anywhere from the wall itself up to the midline. And so if you only solve your equations in big chunks, say you only solve it like at the halfway point and the midline, you're not going to get all of that detail that happens in that rapid change. You want to see everything. So you're effectively refining your, what's the word that I'm thinking of? Your resolution, if that makes any sense. Like if you think of measuring something with a tool, you want to make sure your resolution is as low as possible so that you can see all of the details. That's really all we're doing with this. So prism layer adds resolution at those high change areas. And you can adjust the number of them, which is cool. So I created it. We want to go into default controls, change how big our mesh size is going to be. Thinking about like how big, I usually just kind of guess it. It's like a rule of thumb thing when you first do it. But based on our dimensions, I'll say 5 millimeters. Sometimes I'll pick one that's too small and then I have to kill it because it'll take too long. But if you pick them too big, then you just refine it and go again. There's a way to like get the perfect one. You can like calculate it, but I'm too lazy to do that most of the time. Now we can go into scenes, new scene, because it didn't automatically create one. Mesh scene. Now, I should have grabbed the mouse, but that's okay. Use, let's say we want plus Z with X up. There we go. You can like manually rotate this, but I don't have a mouse, so I'm not. But this is what it looks like when you really zoom in. So this is our mesh. So we have broken down that big old geometry. We put it into 2D because we only really care. It should be symmetric. We only really care about this plane. And we've broken it into these cute little chunks. And they should be 5 millimeters-ish. At least that's like what it starts out being. Is effectively the maximum size of these chunks, about 5 millimeters. And yeah, and so it should be uniform-ish throughout our geometry because our geometry is fairly simple. And then if you need to refine it, so you go back up into here and you can just change your base size. We'll go crazy and see one. It might take a really long time and it might kill it, but let's see what happens. No, that's not too bad actually. Yay! Ta-da! See? And now it kind of does, yeah. But now we've effectively enhanced our resolution. So now, depending on your solver, some solvers solve at these vertices, so like the points where it all comes together. Some solvers, it's like a face thing. Some solvers, it's a edge calculation. But you can effectively think of it as at each of these chunks, you're solving those equations to know the details of how the fluid is flowing at each individual chunk. So in theory, the smaller your mesh cells are, so the smaller these guys are, the better detail you can get. However, the smaller they are, also the more calculation you have to do. So there's the trade-off. Is like, how much detail do you actually need versus how much power and time you have? There's the trade. And in our case, we're not doing anything crazy, so I think this should probably be fine. There's ways that you can, be really good. You're supposed to do a grid refinement study where you effectively run your simulation with one mesh size, decrease your mesh size by half. There's different methods, but the one I usually do is you decrease the chunk size by half, run it again and then compare your results. And then you can do it a third time, and then you can see if your solution stays the same if you're making the chunk smaller, or if it significantly changes your results. And that's how you know if you need to keep refining it or not. That's like the concept. Thank you. I appreciate it. I feel like you're like my personal wow button. I love it. So yeah, that's our mesh.
Does it usually improve accuracy to refine the mesh?
It does, usually. So actually, there's another modeling methods trade-off here. You know your two basic errors, your round off and truncation error.
Mhm.
So the more refined you get, and the smaller and smaller your cells get, the closer they get to zero, the more you're going to have truncation error and
What
round
error?
off error. So, well, it's actually really round off error, right? That would, okay. So now getting back into modeling methods. I can't escape it.
You said a big word and I didn't understand it.
That's fair. I was really like, I knew he'd taken modeling methods, but you guys haven't. Well, you have. But so in numerical methods, when you're solving equations on a computer, you're approximately solving them. You're not precisely solving them. You're like getting an estimate. You have two main sources of error that can make your answer wrong. So you have truncation error and round off error. So truncation error is effectively when you have a big equation. So Taylor series is a big one here, which is a really long equation that you don't necessarily need all the terms for to get approximately the right answer. Like for example, in your derivative. So you just kind of chop off the rest of the terms and you only solve for some of them. That chunk that you threw away, that's going to be error. So that's one type of error. And then the other one is computers can only store so much information about a single number. There's a whole science about it. It's really ugly. But effectively, you have to round the number at some point. And so the smaller you get, the closer to zero you get, the more impactful your rounding is going to be, if that makes any sense. So as you get a smaller and smaller mesh, you're going to have to, or at least your rounding is going to get more and more impactful. And then you're going to be doing even more on top of that. You're going to be doing even more floating point operations because you're now going to have even more and more equations that you're solving. And so it kind of gets compounded. And so that's why you usually want to do a grid refinement study and you run it with a bunch of different mesh sizes and then you can plot your result. And optimally, you would want to look for where the slope becomes zero and then you cut it there. Because then if you keep going, you risk it coming back up. So you want it to be like at that flat bit.
And it usually does flat out.
It does. Almost always, unless you messed up something. Or if for some reason you have an insanely volatile is not the right word, but like in your system, if you have a lot of rapid changes on a super small scale, but also your area of interest is really big, then it can get really, really challenging because then you're also having to do a ton of computation. It's a mess. So that's why I like biomedical engineering because we have a small little area of interest. Even if our shapes are not very fun to work with, they are at least small.
Preach.
Yeah. And it's internal. We love internal because our boundary conditions are easier. But anyway, so yeah, that's our mesh. There's a whole lot of science that goes into that too, but I'm not going to get into it because y'all don't need to have your brains melted today. Kasab has really interesting conversations about it, but you can ask him about it. So let's see. Yeah, we've set that up. And when you run your mesh solver and you generate your mesh, it should create a continuum for you. If it doesn't, it might, like you might have to do it manually. But you now have your physics continua. You want to select your models. So in this one, we're going to do steady because the first one we want to make it easier. So we'll go steady. Steady meaning it doesn't change in time. And then we're doing a liquid because it's a blood-ish. And then we're going to do the segregated flow model. There's also coupled and viscous flow. I read into the documentation because I think Yusuf, you asked me why. we use the segregated model and not viscous or coupled.
Yes.
There's a whole lot of jargon that I was like, you know what? If you guys are interested in it, you can read about it. I really don't feel like talking about it. But just know that it's like one of the fastest ones and the less computationally intensive. So we usually use the segregated flow model.
But to be more realistic, it probably has to use viscous.
I think so in our application because we're using viscous fluids. However, honestly, I wouldn't trust my answer 100% on that one. I would ask like Kasab or Ray Prather. Really, Ray Prather, Dr. Prather. He's the expert. But then we're also going to use constant density. Our density is not changing in this case. So that's the model we'll stick with. And then we're going to assume laminar conditions for this because it's easier. We're not going to get into turbulent flow models. And then I think that's it for all of our models. There's a whole bunch of other ones. Like Lagrangian multiphase is really cool because it helps you do particle tracking. Like if you have things floating in your fluid, you can track them. Mesh deformation, if your shape's changing, it's also cool. And a bunch of other stuff. But we're going to stick with just these for now. So then we go under our models. We already specified our fluid conditions, right? So you want to go under our liquid. This says H2O because that's just default, but ours isn't really H2O. You can rename it, but I'm lazy. I don't want to. So we said that this is 1060 kilogram per meter cubed, and our dynamic viscosity was 3.5 centipoise, so it should be 0.0035 Pascal seconds. And all of these should be good. I'm going to save it because I'm paranoid. I recommend saving periodically because I've definitely made the mistake of not, and then it crashes, and then you want to cry. And nothing gets saved because Star does not autosave at all. But yeah, lost my train of thought a little bit. So we've got our geometry, we've got our mesh, we've set up our continua. We do now need to give our regions conditions. So we've got our boundaries, our inlet, our velocity inlet, physics value. So we now have to tell it what our velocity is. What did we say? 0.3? Yeah, 0.3 meters per second. That's our inlet velocity. And I think because of our outlet, yeah, it doesn't have. So normally you'll have an outlet, for example, you'd have like a pressure outlet is the most common one we use, and you give it a pressure. In this case of an outlet, we're letting it just be an outlet, and it can solve it from there, especially on such a simple geometry. But usually you'll want to give it like a pressure. Yeah, okay, so then from here, we want to make some scenes, because if we run it now, right now, we won't be able to see anything. Like there's no output, none of these pretty plots that you see all over the place. So we got to make some. Let's start with scalar. We'll do a velocity scene first. Usually, I never use this side of the tree, but sometimes it's fun too. So under our scalar here, we have to make sure we have our parts in here. Go select all of them. And then choose our scalar field. So now we want to go to velocity, magnitude. Okay. And then we select here, you can go in and change the contour. I like to make it smooth filled because it looks prettier. I think I'm good.
Is that background noise?
No, have some elevator music playing or something. I think I'm good. Okay, let me make sure we'll check it by initializing. Excellent. That's another kind of numerical methods, but also programming thing that you also should kind of know about by now, maybe.
What?
Initializing your functions or variables. So this green flag initializes your solution. Effectively, what you have to do with computers is when you create a variable or a function, usually a variable, you're creating something. you want to assign it a value, usually 0, to initialize it.
Uh-huh.
Because if you don't, your computer has like allocated that memory space for other things, and so sometimes it will give that allocated memory space to that variable instead to start with, because you didn't give it a value, you just immediately started working with it.
Like you have to set it before you can change it.
Exactly. So you have to, like, it's effectively assigning memory to your variable. You're saying, like, this is a thing that I'm going to make, and computer, I need you to allocate this memory, and for now it needs to be 0. And if you don't do that, it gets all wonky, because you could get random numbers. So yeah, you always want to initialize it. I also like initializing because it helps me to make sure I set up my scenes right, because it should be blue if it's all 0.
Is it the same when working with SolidWorks?
No. So SolidWorks is like just making the shapes and geometries. You can do SolidWorks. There is SolidWorks like FEA, which is the solid version of CFD, where you're looking at like forces on solid objects and how it changes them. But to my knowledge, I don't think there's like any initialization or anything like that in SolidWorks. It's just like you're making fun shapes. I like SolidWorks. I think it's pretty great. Yeah, if you ever need to make a scene so you can visualize what your field of interest looks like, that'll be under geometry. Mesh shows you a mesh scene, which we already have those two. Scalar will plot any of your scalar functions. Vector is also your vector functions. I don't actually know what empty does. I don't ever use it. But most of the ones I use are scalar. So we should probably make sure we should rename this guy so we don't mix them up. This should be scalar velocity. And then for our second scalar scene, which we can pop over to the plot view, under our scalar tab, make sure all of our regions are selected. Our scalar field. So yeah, these are like all of our scalar functions that are built into Star. You don't have to make them, which is gorgeous. You can go crazy. We'll do a pressure plot. There's some other ones like wall shear stress that are useful, velocity. But for now, we'll just do pressure. We'll rename it. Pressure. And then we'll make it. And I wish it didn't do this with the orientation. Why did it stop
Are
it?
you doing the 3D one after?
Yes. Why was up?
No, I was just curious.
Oh, okay.
Because it
Fair.
would be interesting to see like the difference.
Keep having to do this. Plus the X up. There we go. So it still should be 0. Now, you can do more scenes, but for now, I like this. And then last but not least, it needs to know when to stop, right? As of right now, we have it just like after a certain number of times it solves all these equations, we'll have it stop at 1,000 is currently what it's at. You can increase that number if you want. But what I like to do is I go under monitors. It monitors continuity in your X and Y momentum. So it monitors your conservation of mass, conservation of momentum, those equations. And you can set it, I usually go like this. Yeah, I select all 3 of these. Create stopping criterion from monitor. And then minimum limit. So you give it a minimum value, each of those. I believe it's their residual, and you can specify any value. I usually go default 1 times 10 to the negative 6, just to make sure it's like really accurate. It might make it take longer, but I think it's better results. And then, yeah, you can also make plots from these if you want to see how they look, which, why not, we'll do that. And we'll make them all 3 on the same one. Create plot for monitor. Single plot, since it's easier. And then we should be all set to go, I think, I hope. So to actually run it now, we've already initialized it, so we can go to, I'll do it again, just for funsies. We'll hit run, which is the little guy running. I love it. I think that's so cute. I love it when companies like actually do that. So this is your residuals, which are effectively, in modeling methods terms,
Let's go.
yeah, you know what that is. Effectively, in practice, how far off your answer is from what the answer should be. But in iterative methods where you don't have the exact answer, it's like the difference between the answer you got last time and the answer you got this time. So to see how far off they are as you're stepping forward. And so if it's working, it should be converging like this, converging meaning coming to a solution. And we set our values such that it should be done at a certain point, which our residuals of our continuity x and y have reached sufficiently low quantities or values. So we say this is good enough because we won't ever technically have an exact answer. So this is good enough. And then now we can look at our pretty plots. So this is what our scalar velocity plot looks like. It's so big, so it's like kind of hard to wonder. Excellent. I can't click and drag. Okay. So do you guys now remember? Whoa. Remember that cute little graphic I was showing you before where you had those profiles? Do you kind of see how it starts off like kind of flat-ish and then it gets more, but now it starts to look inverted, but it's the coloring. Effectively what you have going on here and why it becomes that more and more parabolic shape is because you have these walls, it's slower because your wall isn't moving. And then everything kind of near the wall, it's the boundary layer, is wanting to kind of stick to the wall and it's thicker. It's not actually thicker, but it's in essence trying to stick to the wall. You have an acceleration through the middle because you're going to have a certain amount of flow velocity. We already said it's going this fast through. Well, if the outsides are slower, it's going to have to even out so that everything gets pushed into the middle and it accelerates through. So that's why you have these cute little colors. I think they're pretty. And then you can see, oh, geez, it zooms in so fast. We'll just, how much did it zoom in? Oh my goodness. Okay, we're gonna, please, no, it just hates me. Okay, I'm stealing a mouse. I had one over here and it disappeared. This janky Apple mouse that I have no idea where it came from. I'm gonna use a dongle. I hate this. Okay, are you gonna be nicer to me? Are you not gonna work? Oh my goodness. This works, but the scroll doesn't? Okay, we're gonna go crazy. We're gonna do this. Ugh. Okay, no, it does work. I was just so zoomed in. Okay, we're gonna look at it vertically because I don't feel like rotating it. But you guys see how you have this gradient? So the blue is slower. And fluid dynamics principles, you have what's called the no slip condition. So if fluid is running along a stationary surface, stationary object, that layer of fluid that is touching the wall isn't going to slip past the wall. It's going to kind of effectively stick to the wall. So you're going to have slower flow on these edges, and then you have the gradient of it getting faster towards the core. So, make sense?
Mhm.
Yeah. You guys are getting like this massive crash course into fluid dynamics, even though you're never going to have it in your coursework. But yeah, so I think that's neat and a useful thing to have. And then we also have, we can look at the pressure one. This one doesn't matter as much, but it's kind of fun to look at like how you have that high pressure coming in, and then it kind of resolves itself to a lower pressure as you get out towards the end. Yeah, I think that's it for like this tutorial. And then if you want to like save any of these, you just like right click on the scene and then you can say hard copy and then it'll save an image of this cute little guy. Mm-hmm. Anybody have any questions with this fun, cute little tutorial that kind of took a long time? No? Okay, excellent. And then I'm debating on whether or not I want to start from scratch with the next one, or if I just want to talk about the next one. What do you guys, which one would you rather do? Do you want to start from scratch again for the next one? Or me pull out the one that I've already done and then I just kind of talk about it?
I'm fine pulling out the one you've already done. I agree.
Okay, I guess it's more of like a how much are you planning on actually doing this at home, really? Because if you want to follow along with the second example, is the most applicable to what we do here. It like is what we do here. This one you don't really do here. This is just like intro to CFD. So what do you still same answer? Okay, we'll just pull out the one that we've already made, and then if there's concerns, then y'all can like message me or whatever. Open, browse. I put it under the folder that I need to give a name. Yeah, tutorial 1. Okay, I'm gonna close all of these. Okay. So, is this the? Oh, I'm still in the other one, the wrong file. Close this guy so I don't mix it up again. Save. Okay. Okay. So this is your carotid artery bifurcation. So this guy here should be your brachiocephalic trunk. And then you also have your, I'm always forgetting which one's which. One is your carotid artery, your right carotid artery, and then your other one should be your subclavian artery, which I guess I can find out if I just cheat. And I go like this, because I set it up last night. Parts, surfaces. Okay, your little baby one's your carotid, and then your big one's your subclavian, I think, according to what I did at midnight last night. This is, so you have two carotid arteries, you have your right and your left, that are on either side of your neck. This brachiocephalic trunk, though, actually comes directly off your aorta. It is the first, like, shoot off in the arch. And then it splits into carotid and subclavian. Subclavian goes subclavian, subclavicle below your clavicle, and then gives blood to your arm. And then carotid goes up, and I don't remember where it goes actually. Oopsie. But in effect, this is like the real world example. And we've had people actually look at this. We have at least one master's thesis on it. I don't think we have any of the posters in here.
Not our poster.
No, that's on your LDAD. Oh, okay,
Yeah.
okay, my bad. My poster got kind of hidden because I had moved the bookshelf back there and it's too tall.
Oh, it's behind the bookshelf.
Mm-hmm. I was tired of the fire hazard being in our walkway, so I moved it. Steve caught me trying to move it by myself. It wasn't going good. But anyway, so we've had students study this in the past. Usually we use FSI, fluid structure interaction, which looks at, how a fluid and a solid interact with one another, like how a fluid can deform a solid, but also how a solid can deform a fluid, both directions. It's an interplay. Most of the time we just look at the CFD though. When you don't have a deforming wall, you can usually just look at the CFD. So in our case, we got the same fluid properties. And then, so I did the same process, except this time when I got my geometry in, I had a file already, and then I did file, import, surface mesh, and then it was this art1 right, and then I clicked it and I hit open, but I'm not gonna import it again. So it's an STL file. And then this one is harder to separate the surfaces because I had to go here, actually no, it was here, split, and then I had to do split by angle. And so you can specify it's the minimum angle for it to split two surfaces. And I think I had to go all the way down to like 39 degrees for it to finally split all four of these. And then I renamed all of them, which was a serious pain. But that is what it is when you're working with biomedical shapes. So And then our operations, we did an automated mesh. You didn't have to badge it this time because I did it 3D. It was just new mesh and then automated mesh regular this guy. And then let's see, what were my default controls? Base size was 1 millimeter this time. I should probably specify. I only have 2 prism layers. I think that's kind of lame. We're gonna give it 8. Boundaries. Okay, so in this case, we have our boundaries. To talk about them, you guys have seen the circuits that are all over the room, the electrical circuits on these posters, right? They're what we call lumped parameter models. Really fascinating scientific concept. Somebody someday, I don't even know who made the first one. Somebody was like, you know what's crazy is electrical circuits and blood flow through the body are governed by effectively the same equations. So you can create an electrical circuit that can solve for, really it's an analog. So you can solve for the voltage, current, E equals IR. Resistance, you give it a resistance. I had to remember that. Wait a minute, what's the, yeah. And by using a series, whether it's in series or in parallel, but using capacitors, resistors, and sometimes inductors. You don't have to have inductors because they make it increase in order of difficulty. But if you put all these circuit components together, you can pretty accurately model how blood flows through your body, because your arteries, they act as capacitors. So Kasab has a really cool discussion about it, and I recommend talking to him about it if you can, because he blew my mind when I talked to him about it, because he was relating electricity, fluid flow. I think he brought in electromagnetism and heat transfer. They're all interconnected. So I was like, dang. Yeah. I had to just like sit there for a second because I was like, what? But it's a fascinating concept. So like capacitors, in essence, what they do, they store excess energy or electrons, right? Just like arteries, they expand when you have a high pressure. And then when your pressure decreases, they contract back out. And what that does is it kind of modulates your internal fluid pressure flowing through your arteries. So that way you kind of have a constant pressure. And because your heart is pumping, it's pulsatile, it's not constant, right? You're not having the same pressure flowing through. It kind of helps negate some of the pulsatility in that constant rapid change. So it acts as a capacitor. And then inductors, they really just model like your inertia of your blood flow through your body. So they're not super necessary, but they make some calculations easier or harder, depending on how you look at it. And then fluid flow, and this goes like deep into fluid concepts. But if you calculate the resistance of blood flowing through a pipe, the equation is identical to electrical resistance. So you have in your body a resistance in your vessels that is the same. So you can set up this electrical circuit. At the end of the day, you can get mass flow rates, so the amount of blood flowing through different parts of your body, and you can also get pressures. This should be its own like lecture in itself because it's huge and it took me a really long time to learn. But you can get those two important values. You can also get volume, but that takes more. It's really mass flow and pressure. And then you can take those values that you calculate in your circuit at any point, and usually you'll have to open it up if you want to couple the two together. But in our case, I didn't. I just said, at this point, I'm going to calculate with my circuit. That's a circuit that one of our grad students way in the past made. We're going to get our mass flow coming into this chunk here, coming in right here, and then calculate the pressures where it's coming out, also from that circuit. And then we're going to assign those values to this. And this is now unsteady. So this is not a steady state simulation. Last one we did was steady. We just assume it's a constant, same flow going through the whole time. This one, not steady. Because in real life, especially in your body, right, it changes. Your heart is pumping, it's time dependent. So with my circuit, I say mine, it's not really mine, it's kind of mine, not really mine. I have it outputting data in this massive Excel sheet. And this star can take in all of that data in a table, which is down here, this boundary conditions table that I imported. Yeah, I won't continue on that one too much because I feel like I will melt your brains if I keep going onto it, and it's really just not that fun. But in essence, that's where our boundary conditions came from, right? Because we still have a mass flow inlet, and we have two outlets this time. They're both pressure outlets. And then when I assigned them values, I went into values pressure. I gave it method table time, and then under the time little node there, I specified what column in that table it's getting its values from. And then I think I only set up these scenes, which is geometry, scalar pressure, scalar velocity. Did I give it a vector velocity? I did. How cute. Okay. The vector stuff is a lot easier to do when you actually are doing a 3D simulation. The other one we did was only 2D, right? Vectors are typically used in 3D space. But another thing I did, so it's a lot easier if you make a derived part to analyze 3D simulations. So I made a plane section. That's just under, like, if you right click here, new part, section, and then plane, you can change what direction your plane is. So that red box is what your plane becomes. I think I made it, actually it's probably 0, 1, 0. And I think I had to modify it. Yeah, I had to move it around because it needed to be in the middle, and this thing is not perfect. But my other one is actually down the middle. But anyway, so making that plan makes it a lot easier. Got that I have this to analyze and create all of our cute little scenes, if you will. I don't even think I finished running this. So I'll go solution, clear all, initialize, and then run. But what I think is really fun is to, like, watch it as it's kind of running. Now changing things as it runs is not very easy, so you almost always want to just stop it and then make your change. So we can do this. I'm gonna go this because it's kind of ugly. Why'd you right click? Smooth filled, and that looks a lot prettier. And then you can resume the simulation. But this, I think, is stepping forward really slowly in time. Yeah. It's like 0.001 seconds. So with unsteady simulations like this one, you have now two iterations, two like loops of iterations. So when I say iteration, I just mean each time you're solving your equations. But now this has to loop and solve at the same time until it gets to the level of accuracy you specified. And then it has to step forward in time, do another iteration on that outer, and then loop again at that same time step until it gets your level of accuracy. So there's a lot more computation that has to go on when you do unsteady because it has to solve it multiple times per time that you give it, if that makes any sense. So in theory, you should kind of see how this middle guy's changing. You can kind of see the pulsatility. This is supposed to be heart flow. I don't think this one's super dramatic. I don't remember why. Because it is coming right off the aorta, so you should really be able to see it. But it also could be that it's really slow. But yeah, that's the majority content. Other than, like, looking at, so it's important to see another fluids concept. So when blood flows through the body, or really just any fluid flows through a pipe, but it's applicable with blood flow. And so you guys were talking about this, how you have, like, your capillary beds. And so you start out with your heart and your aorta, big old vessel, aorta. But then eventually they get down to those super teeny tiny vessels. Well, how do they do that? They have to branch. Branching is technically not great from a fluid standpoint because so you see how you have those blue pockets? So what's really happening in here and also at that peak here is you're forcing the flow to separate, and when it's being knocked out like this, it comes around, and then in here it's swirling. So you have a low velocity because even sometimes it's not fully going forward. It gets stagnant in here. And what happens when you have stagnant blood flow? You get clots. So we actually did this in one of my grad classes, Kasab's grad class, of course. We calculated the optimal bifurcation angle, so this bifurcation, right? You can calculate the deviation from the midline of each of your branches to get an optimal like scenario. And the beautiful thing is nature does almost that optimal branch every time. And it's usually like in disease cases where you'll see it be suboptimal. But in normal healthy cases, it's usually very close to that optimal angle, which is really fascinating. Who knows?
So then the probabilities of having a blood clot is higher.
It's higher if it's not at that angle. It's everybody's gonna have some, right? Because you have to
Yeah.
have branching. Because otherwise it's not gonna be able to get to all of your tissue and come down to that scale. And so we try to minimize it.
Yeah.
Our bodies do by getting that optimal angle. But yeah, it's still not perfect. Because then also there's like wave theory that goes into this because it's pulsatile flow. It's really ugly. The equations are awful. We had to do them in that class with Kasab. Because it has to do with how the pressure wave travels through the vessels and then how it gets reflected. So if you have, I always pictured it as like a sound wave. It's the easiest to think of. So you have a sound wave traveling through a pipe. It's just going to kind of continue on down the pipe, right? Well, if you have a split and there's like this wall in the middle where it splits, that sound wave is going to hit that tip and bounce back. So you have effects of pressure that come back up your bloodstream at these bifurcations. It's really fascinating. That's a tangent also.
It's still going.
Yeah. And it will go for a very long time unless I stop it because I think I have it going for like 3 seconds and it's only at 0.4 seconds. That's why you want to run this on the cluster. Every now and then you'll see a time. See that? It's like right here. I'll just stop it. Boop. Right here. 0.4 seconds. Yeah. And so every time, see it's stepping forward in time, it's already at 402 time steps where it's had to iterate and then step forward in time and then iterate and then step forward in time. So yeah. And it's interesting to look at the residual plot too, because you can kind of see it. See, each of these like jumps are where you're going to see steps in time where it's going to have to reset or it's changed in time and it's solving. So then the residual will go up as it gets farther away and then it comes back to an answer. Then it jumps away and then it comes away again. Back. In a perfect world, it would not get this high. But alas. And then I think I guess the last thing we'll talk about is so let me close all these because it hurts my brain to see all of them open. So solution histories. So when you have an unsteady simulation like this, if you have just a singular snapshot in time, so say we just have this guy, that doesn't tell you all that much, does it? Because you have a different answer for this at each time step. So one thing that's really useful to do is you create a solution history. We're gonna give it a name, we'll just call it history. That's usually what I name my files too, not super descriptive. Now this will record your answer at each time step, which also makes it take even more time, but it makes it so you can actually see what happens in all of these. And then you can change like how often it saves it. You can make it not go every time step. You can make it be like every 10 time steps if you really don't care that much. And then when you go into history, you have to choose what functions it's going to save. For most cases, it's ideal to only pick the functions that you're interested in knowing the outcome to, and then any functions that might be dependent on, or that those functions might be dependent on, if that makes any sense. So like, I think we care about any of these. We don't need density because we're constant density, viscosity. And there's a lot of these that like you really don't need to know that much. Like some of these are like for turbulent flows where you have a turbulent solver, and that's useful, but we don't have those. Pressure, why not? Pressure coefficient, it's dependent on pressure.
I'm gonna go to the bathroom. I'll be back.
Okay. And then you want to save all of your time variables. Also, I don't think I want to do total pressure. Velocity for sure.
Sorry.
Wall shear stress. What are all my scenes here? Oh, it's gonna make me do this first. That's great. Okay, I think it's all of these, but I can double check my scenes. Pressure and velocity. Okay, those are the only two. And so then when you run it next time, so we'll say let's don't do that. I just have mouse. Save it. We'll clear our solution. Also clears the history solution. But now next time you run it, it will save it every time step. And then hello. Okay, there we go. We'll let it do a couple. Am I crazy or is it? Okay, no, no, it is changing. And we'll stop there because I don't really feel like doing that many. It's already at. Actually, I don't know how many. We'll find out. We can do this. We can go crazy. We can add an annotation in here. Ooh. Also get the solution time. I'll put this guy. So that's a useful tool if you can annotate your scenes. And so then now, if you go into solution views, solution history, you can select what time step you want to look at, and then to change your scenes, you have to go into what are we looking at right now? Scalar view. Yeah. So you have to right click, apply. Yeah, representation to displayers, and then you choose that history file that you created. Did I not save the proper? No. Stop it. Oh no. Oh, okay. I forgot a critical thing, and this is a good teaching lesson also. So I selected the function, but I did not select the inputs. I usually select all of them. I think I only need plain section for this, but now I gotta do it again. Yeah, I do this all the time, and I always forget. Okay. Okay, we'll call it good. There.
I was like, where's your picture?
Yeah, it's because it hadn't updated it to reflect the history. Okay, so now under solution views, you can change what state you want to look at, aka what time step you want to look at. And because we annotated it, we know exactly what time it was in our solution. And you can make cute little graphics, so we can stop right clicking. We can play it and then screen record it, especially if it's longer. That one's like kind of fast. I think you can change how quickly it goes through, but I always think it's so much fun to just be like, so yeah. I think that's mostly everything, at least with this one. Questions, comments, concerns?
There was like a point where it like went blue like on the bottom lower side of it. But it was like the first time when it had been running for a minute. Why does that happen?
Blue.
Like
You're talking about when it was like here?
kind of yeah, but like it was like just that side, like the one closest to us, and it was like the first run. Like when it had been going for a minute, like it went blue all of a sudden. I was just kind of confused, like how that.
Oh, okay. So that would probably have been at one of the periods in your cardiac cycle where you're not actively pumping blood through your aorta. So
Oh,
like
okay.
probably, I'm guessing because I don't know exactly which scene, but I'm gonna guess it's probably one of those. So like when your heart is filling, for example, and it's not expelling, it's not in the ejection periods, relaxation. Um, there's no pressure to drive the flow up through your aorta and through here.
That makes
So it's
sense.
gonna relax. And you actually have some backflow
Okay.
in some of your arteries where if it's in that filling part of the cycle, well, there's some delays, whatever. Um, there is backflow. I think also in the aorta too. I think if I remember correctly. Um, so you'll have low pressure, low flow velocity.
Okay. And then, so like when you had like the 89, like the value.
Thank you for grabbing it. Hello, welcome back.
How did you like get the values like the 89 and like well it's like at the beginning when you were showing. Is there like a formula for it or is it just like you just put it? When it was like 89 and then you said you had to put it down to like 39 or something.
Was it like the fluid properties where it was like 1060 and 0.0035? Or was it
Maybe it was like the
was it when I was creating the plane?
no, not the plane that you were like shifting. It was like maybe the geometry parts. I'm not sure.
No, you're good. I'm just trying to think through like what I've given values to. See, there's the mesh size. That's a value. Boundary conditions. I didn't give these boundary conditions a value though. Here's my stopping criteria where I set it to 1 times 10^-6.
Maybe it was a mesh size. Maybe
Was it mesh size?
Was that the last one that you did like 5 and then you put it down to like 1?
Talking about the number of prism layers? Okay, here, wait. I'll try to run it back. Let's see. Oh, it looks like this is not up to date. Yeah, you get a cute little warning triangle if you haven't run your automated mesh. Okay, this needs to be stepped forward. Perhaps so I can finish. Can I execute? Yeah. So are you talking about like here where I gave it 1 millimeter base size for the grid where it's the, where's my, do I not have a mesh scene? What on earth? Okay, look how pretty she is. Keep reading that I literally grabbed a mouse for this. Because it could have been that. It could have been also, actually it has default controls. Number of prism layers, so I changed it from 1 to 8. Was it this one?
No, I think it was a bigger number. It was like the very beginning of when you pulled up the 3D. And it was like a pop-up tab or something and it was I think it stayed 89 but you had made some sort of comment how you had to bring it like down to 39 or something.
So import, and I talked about this. I didn't open it because that gives you the thing. Very beginning, and I said I had to reduce it.
We're just all struggling
I
so
know.
much trying to figure this out.
It wouldn't have been okay. Let me look through all of our chunks here. I need to execute this again also. Okay, because my workflow is you import the geometry. Oh, I know what you're talking about now. You're talking about splitting the surfaces, right? Where I was talking about how like I imported this thing and then you have to split by patch. Just kidding. It's only consists of one patch. I don't know if it'll let me. Or no, not split by patch, split by angle. And then this
Yes,
is 89. And then I had to,
yes.
So honestly, this defaults to 89 degrees.
Okay.
And then sometimes you can have a model and you'll import it and then you're trying to split it by, you have to go split by angle because most STLs are not in patch, like form. So you have to go angle, split by angle, and then sometimes it'll work and you just run the 89 and then it'll split it. The moral of the story is that you need to have a separate face for your wall, your outlet, or outlets plural depending on how many you have, and then for your inlet, and they have to be separate surfaces in here. And so I wonder if I can just split my angle again. And then if it doesn't work, then I just like reduce this number until it does work. Like, see what happens if I do 5, just for funsies. Oh my, yeah. So then it splits them into all of these sub walls. We didn't really want to do that, so we can go like this. Okay. There we go. It's because I gave it 5 degrees because it makes it more and more like sensitive in effect. And we're just gonna combine them all back up. Ta-da! But yeah, so I usually will start with the 89. If it doesn't split it into the number of surfaces that I need it to be, then I'll just reduce it by 10 each time until eventually I get it into my ones, or I at least have the ones that I want, and then I'll combine if it did extra. Which can be a pain because it's really just like rule of thumb. There's not, or not even rule of thumb. It's just like the vibes. You just have to hope for the best. Why is it making me execute it again? Was it because I messed with the surfaces? Probably. But yeah, she's cute. This should probably be refined even further. These chunks are kind of big. And that's also another thing is like you can usually tell, especially in these scalar plots, like you see how it's got those clear chunks. That is your mesh. Like those are the edges of your cells. So if you can clearly see this, like that's way too big, then you'll kind of know, like I really probably should refine it. Or if you really just can't refine it, then you'd be like, hee yeah. But you honestly, you always should do a grid refinement study, just for good practice, even if it is annoying and it means you have to run your simulation 3 times. That's what it is. Yeah. Any other questions?